welcome to the second session of Power Electronics. Today's topic of discussion is TRIAC. So let's see what are the contents of TRIAC. So first of all, we are going to look at the construction of TRIAC. Then we are going with different modes of operation with the TRIAC. Then we are going to look at the VI characteristic of TRIAC, and finally we are going to compare TRIAC, DIAC, and SCR so that we can understand the similarities and differences between these power devices. So let's get introduced with the TRIAC. So TRIAC was basically invented around 1956 to 1960s by General Electric Company. It is the same span in which the SCR, DIAC, and TRIAC was invented. Again, this device belongs to a thyristor family as it is a multi-layered and multi-junction device. The TRIAC is an abbreviation that stands for triode that works for AC. So majority of applications of TRIAC are in AC supplies. TRIAC is a three-terminal device which the terminals are named as main terminal 1, main terminal 2, and gate terminal. MT1 and MT2 are similar to the DIAC, whereas gate is an additional terminal which gives us a feature of controlling this particular device. So the user can turn on this device at a particular desired or at a desired point. Now the device is manufactured in a manner that the gate terminal is manufactured closer to the MT1 terminal as compared to the MT2 terminal. Now to perform all the measurements like voltage or current, the MT1 is used as your reference terminal. Now, to best understand the working of TRIAC, it is considered as a reverse parallel arrangement of SCR. As we can see from the diagram, the two SCRs are connected in reverse parallel arrangement. So, the one SCR can conduct from MT2 to MT1, the other SCR can conduct from MT1 to MT2 with a common gate terminal. So, basically, to understand the ideology and the working of TRIAC, it can be considered as a combination of two SCRs that are connected together in reverse parallel arrangement, so that the current directions can be understood for this particular device. Now, the TRIAC exhibits the forward characteristic of SCR with gate terminal in first quadrant as well as in third quadrant, obviously being a bidirectional device. Now, as we have mentioned in the introduction, it is a multi-layered and multi-junction device. As you can see, there are 5 junctions are available and multiple layers are available. Now, it is manufactured in a manner that the gate terminal is closer to the MT1 terminal, as we already mentioned. Now, the circuit symbol clearly indicates that it's a bidirectional device in which the current can be carried from MT1 to MT1 and from MT1 to MT2. The gate terminal obviously gives us a controlled feature so that we can turn on this device as per desired point. Now, this is one of the TRIAC which is available commercially. It is BT136 with a rating of 600 volt and 4 amperes. So, majority of commercial or AC application, household application uses this. For our AC fan regulators, it is majority of times it is employed. So let's jump to the in details of working of this particular device. So the TRIAC works in 4 modes. Now, as we have discussed in the DIAC, there are 2 modes of operation: MT2 positive and MT2 negative. Now with this TRIAC, there are 4 modes. With MT2 positive, with that the gate can be positive and gate can be negative. Similarly, with MT2 negative, there are 2 modes, again gate positive, gate negative. So there are basically 4 modes of operation: mode 1, 2, 3 and 4. Among them, mode 1 and mode 4 are having majority of commercial applications or commercial uses. So we'll emphasize on these modes particularly, but we'll learn all them together. But majority of application uses mode 1 and mode 4. So let's get in detail with these workings. So let's start with the first mode. The first mode is MT2 positive and gate positive. As you can clearly see from the biasing, the MT2 is connected to positive potential with respect to MT1, whereas gate is also connected to the positive potential with respect to MT1. Now, because of that, junction J1 and J3 will be forward bias, whereas junction J2, J4 and J5 will be reverse bias. Due to the reverse biasing of junction, now we are not going to consider J4 and J5. Now, as junction J1 and J3 are forward bias, the charge carriers get transferred within the device. But as junction J2 is reverse bias, all the charge carriers get accumulated near the junction J2, which increases the width of depletion region of J2. And as width of depletion region of J2 increases, obviously barrier potential will increase. And as barrier potential of the device increases, there will not be any movement of charge carriers from N1 region to P2 region or from P2 region to the N1 region. As there is no movement of majority charge carriers, the device is said to be in off condition. But there will be a minute current due to the minority charge carriers called as leakage current that will be flown through the device because of the charge carriers which are available in depletion region. So very minute current, or it is also called a saturation current, because it has a constant value that will flow through the device. Now, as gate is connected to the positive potential of battery with respect to MT1, now there will be an establishment of gate current that will be established from positive through gate through P2 through N2 through Mt1 through negative, it will be grounded, and because of that it injects charge carriers directly in the junction J2. And as the charge carriers are directly injected in junction J2, it reduces its barrier potential. As the barrier potential of junction J2 decreases, suddenly the avalanche breakdown of junction J2 will take place. As soon as avalanche breakdown of junction J2 will take place, there will be large rise in current or large movement of charge carriers are observed, and suddenly the current will be established. So current will be established from Mt2 to Mt1 with a path of positive Mt2, P1, N1, P2, N2 through Mt1 through negative, it will be grounded, and there is a sudden rise in the current. And as soon as there is a large flow of current, the device goes to an on state, and whenever the TRIAC goes in on state, just like SCR, it jumps to a lower voltage state or lower potential state, so maintain a minimum voltage drop across it, allowing a large current to get established. That we can see from the characteristic as well. Let's see the characteristic. Now in this mode, in this mode 1, the Mt2 is connected to the positive potential. So we can clearly see that we are in the first quadrant, in which as soon as the device goes in on state, there is an exponential rise in current which we have observed. Now as we increase the gate current, as we can clearly see from the graph, as we increase the gate current, suddenly the turn on point of the TRIAC goes on decreasing, similar to the SCR with the gate terminal. Same characteristic is exhibited. Now as Mt2 is considered as positive, we are considering the voltage and current flowing across the device or flowing through the device is positive. So this is the basic working, similar to the SCR with the gate terminal. So mode 1, we can say that it is similar to the SCR with the gate terminal, the forward characteristic. Let's start with the mode 2. In mode 2, now Mt2 is connected to the positive potential, whereas gate is connected to the negative potential. So we are keeping this battery biasing same, whereas we have reversed the biasing. Now because of that, now let's see which junctions will be forward bias, which junctions will be reverse bias. Now junction J1 and J4 now will be forward bias, whereas junction J2, J3 and J5 now will be reverse bias. In previous condition, J3 was in forward bias condition. Now because of the as the polarity of gate is reversed, the junction J3 will be now in the reverse bias condition. Now at junction J1 and J4 are in forward bias condition, obviously they allow the charge carriers to get transferred within the device. But now at junction J2 is reverse bias, all the charge carriers get trapped across the junction J2, which again increases the width of depletion region. As width of depletion region increases, obviously the barrier potential of the device increases, and because of that there will not be again any movement of majority charge carriers from N1 region to P2 region or P2 region to the N1 region, and again we say that the device remains in off condition. But again there will be a minute current due to the minority charge carriers called as leakage current that will flow through the device. Again it will be a saturation current which will have a constant value, but the device is said to be in the off condition. Now as the Mt2, as a gate is connected to the positive potential with gate is connected to negative potential with respect to Mt1, there will be a flow of gate current that will be established from positive Mt1 through P2 through N3 through gate. Because of that, as the gate current is established, it injects the charge carriers directly across the junction J2. As the charge carriers are injected directly across the junction J2, it decreases the width of depletion region. As width of depletion decreases, the barrier potential will decreases and avalanche breakdown of junction J2 will take place. But now even if the avalanche breakdown of junction J2 takes place, but J3 is still in reverse bias condition. So J3 is still in the reverse bias condition. So they will not. So because of that, a current will be established with a path of Mt2 to gate. So a current will be established a path of positive Mt2, P1, N1, P2, N3 gate and negative. Because of that, through which it will be grounded. But now as junction J3 is reverse bias, there is no current established from Mt2 to Mt1. So because of that, we can't say the device yet goes in final condition or goes in complete on condition. So it's, but still there is a production of current. That's why this particular current is called as initial conduction or initial current that will be established. So current will be established with this path. Now the device is not yet still in on condition, but this initial conduction is actually helps the device to goes in on condition. Let's see how it allows the device to goes in on condition. Now because of establishment of current, now what we observed that we observed a potential gradient in the layer P2. The left hand side of the P2 layer is conducting, whereas the right hand side of the P2 layer is non-conducting. So obviously the left hand side will be hooked up to the positive potential as compared to the J3 or higher potential with respect to the right hand side. So what we observed is that the left hand side of P2 will have a higher potential as compared to the right hand side of the P2 layer. So what we observed that the left is more positive as compared to the right side layer. And now suddenly there is a potential difference developed within the P2 layer. and whenever there is a potential difference, there will be an establishment of current, and there will be a flow of current that will be produced within the device. Because of this current, junction J3 will now be in forward bias condition, because more potential is developed across this device as compared to its because of its previously it was in reverse bias condition. So as more potential is developed within the P2 layer, it forwards biases the junction J3, and that is what we need to allow the device to go in on condition. And as soon as junction J3 is in forward bias condition, it allows a final current to get established. So we get a final current that will be established from MT2 to MT1, and that will be flown through the path of positive MT2 P1 N1 through P2 N2 and MT1, through which it will be grounded, through negative it will be grounded, and allows finally to the device to go in on condition. So in this mode 2, actually we observe two currents, two stages of current. First is initial conduction that allows to develop a potential gradient within the P2 layer, and because of forward biasing the J3 layer, and finally allowing the device to go in on condition. So finally the device gets in on condition and produces a current from MT2 to MT1, and that is what we need for this. So let's see for the characteristic again, as the current is again established with the MT2 positive. So we are getting again a positive current and a positive voltage across the device. Again, as the gate current increases, obviously the turn on point of the SCR, turn on point of TRIAC will decreases. Also, as soon as the device goes in on condition, it jumps to a lower potential state, as we can see from the characteristic, and there will be an exponential rise, large rise in the current that will be observed in the device. So this is the similar characteristic as we have seen in the mode 1 as well as. So mode 1 and mode 2 have the same characteristic. The only difference is that mode 1 has direct conduction, whereas mode 2 has an initial conduction and final conduction. So this is all about MT2 positive. Now let's turn the table and let's go for the mode 3, in which now we are going for MT2 negative and gate positive. So now we are switching the MT2 negative. So as MT2 is connected to the negative terminal, now you can clearly see this battery is reversed. We are connecting MT2 to the negative potential with respect to the MT1. Now gate is at positive potential with respect to MT1. Now let's see which junctions will be forward bias, which junctions will be reverse bias. Now the junction J2, J3 and J5 will be forward bias, whereas junction J1 and J4 will be reverse bias. Now we don't need J4 for this particular operation, so we are not going to consider the J4 for further operations. Now as the junction J2, J3 and J5 are in forward bias condition, obviously they allow the charge carriers to get transferred within the device. But as the junction J1 is reverse bias, all the charge carriers get accumulated near the junction J1, and as the all charge carriers are accumulated near the junction J1, it increases the width of depletion region. Again, the same process what we observed in mode 1 and mode 2. As width of depletion region increases, the barrier potential of junction J1 will increase. As barrier potential increases, it will not allow any movement of charge carriers from P1 region to N1 region or N1 region to P1 region. So no movement of majority charge carriers means the device remains in off condition. But we know that there will be a minute current due to the minority charge carriers again, and that will be called as leakage current or saturation current, but the device remains in off condition. So as the gate is at positive potential and it allows to establish a gate current, so gate current will be established from positive through gate, through P2, through N2, through MT1, through negative it will be grounded. Because of that, it injects the charge carriers in the P2 layer that are getting transferred to the J1 layer, as J2 is already in forward bias condition, so they get propelled within the device and directly applied across the J1. As they are applied across J1, obviously they decreases the barrier potential of the junction J1 and allows an avalanche breakdown of junction J1 will take place. As soon as avalanche breakdown of junction J1 will take place, our barrier is removed, so obviously there will be an establishment of current now, but it will be in opposite direction. Now it will be established from MT1 to MT2. So now the current path will be from positive through MT1, through P2, through N1, through P1, through N4, through MT2, through negative it will be grounded, and finally allows the device to go in on condition. Now previously the current direction was from MT2 to MT1. Now the current direction is from MT1 to MT2. So now the current direction is reversed. Also voltage drop across the device is reversed. So now if we consider the first mode 1 and mode 2 polarity is positive. So now as the direction of current is reversed, we need to consider it as a negative polarity. So let's see from the characteristic itself. So as we have mentioned previously, MT2 is positive, the current is established from MT2 to MT1. Now with the MT2 negative, current flows in opposite direction. That's why we are plotting it in a third quadrant. Again, as soon as the same characteristic, as soon as device goes in on condition, it jumps to a lower potential state or lower impedance state, in which it maintains a minimum voltage drop across it, allowing a maximum current to get established. Again, as the gate current increases, the turn on point of the TRIAC will be decreased. So as gate current increases, the turn on point we can decrease for this particular device. So that we observed in the quadrant 3 operation, in which mode to MT2 is negative. Now let's start with the last mode of operation, that is a mode 4, in which MT2 is negative and gate is negative. So again, the battery is this biasing remains the same. Now we have reversed the biasing of for the gate and MT1, in which MT2 is negative. So we can clearly see that MT2 is connected to the negative potential, as well as gate is connected to the negative potential. Now let's see which junctions will be forward bias, which junctions will be reverse bias. Now junction J2, J4 and J5 now will be in forward bias condition, whereas junction J1 and J3 will be in reverse bias condition. We are not looking for J3 junction, as it is not useful for this particular mode. So at junction J2, J4 and J5 are in forward bias condition. Obviously they allow the charge carriers to get transferred within the device. As the charge carriers are transferred within the device, but junction J1 is in reverse bias condition, so all the charge carriers which are transferred within the junction get accumulated near the junction J1. As charge carriers are again accumulated near the junction J1, it increases the width of barrier depletion region, which further increases the barrier potential of barrier potential of the device. As barrier potential of the device increases, quite naturally, there will not be any movement of charge carriers from P1 region to N1 region or N1 region to P1 region. So the device is said to be in off condition, but there will be minute current due to the minority charge carriers called as leakage current that flows through the device. But still the device remains in off condition. This current is also called as saturation because it follows a constant. It has a fixed current or fixed amplitude, we can say. Now, as the gate is at a negative potential with respect to MT1, this allows a gate current to get established from positive MT1, P2, N3 and gate, which injects the charge carriers in the junction from the junction J4 through J2, and which are again propelled across the junction J1, which decreases the barrier potential of junction J1. As the barrier potential of junction J1 decreases, as the barrier potential of junction J1 decreases, the avalanche breakdown of junction J1 will take place. As soon as avalanche breakdown of junction J1 will take place, there will be an establishment of flow of current. The current will be established with a path positive MT1, P2, N1, P1, N4. So the current will be established from positive MT1, P2, N1, P1, N4, MT2 through negative, it will be grounded, and finally the device goes in on condition. So now the current will be established from MT1 to MT2. So again we'll see in a third quadrant operation. So let's see from the characteristic. So again the characteristic clearly resembles that the current flows in opposite direction. That's why it's in third quadrant operation. Again, as soon as the device goes in on condition, it jumps to a lower voltage state or lower potential state, allowing the exponential rise in current. Again, as the gate current increases, obviously the turn on point of the TRIAC decreases. So the characteristic clearly resembles that the device is a bidirectional device, can conduct in both direction, and also it gives us the capability that it can be controlled in both directions, in positive direction, or that is from MT2 to MT1 or from MT1 to MT2. So control feature is available in both the features, unlike the SCR in which it is allowing in only in forward bias region. So let's summarize what we have learned. So we have looked at 4 modes of operation. Among them, as I have mentioned, mode 1 and mode 4 are having majority of commercial importance. Now the best part of TRIAC is unlike SCR, the TRIAC can be turned on by you applying a positive gate current as well as the negative gate current. That is the fantastic part of TRIAC. Also, the majority of commercial applications uses TRIAC and DIAC pair. The reason behind that, TRIAC needs more amplitude in its gate current to turn it on. So that's why it needs a DIAC which can propel the gate current, which can increase the amplitude of the gate current and apply it to a TRIAC. So basically, the majority of application uses TRIAC and DIAC pairs. Let's finally compare the SCR, DIAC and TRIAC. Again, in terms of terminals, if you compare, the SCR is a 3-terminal device, anode, cathode, gate. DIAC 2 terminals, main terminal 1 and main terminal 2. TRIAC 3 terminals, MT1, MT2 and the gate. If we compare on the basis of current flow, SCR is the unidirectional device, whereas among these two, the DIAC and TRIAC are obviously the bidirectional devices. Now if we compare the quadrant operation, the useful quadrant operation we can say, The ACR works in first quadrant, whereas DIAC works in first as well as third quadrant. Obviously, DIAC and TRIAC works in first and third quadrant. Now ACR, yes, works in first quadrant as well as third quadrant, but reverse bias condition, actually it gets breakdown, so it is not used for any application. So we are sticking to the forward bias characteristic only. So that's why we are saying that it is only for first quadrant operation. Now if you go for turn on nature, we the is because of the gate terminals the ACR and TRIAC are having, they are jumps to an controlled category, whereas DIAC, because of its there is absence of gate terminal, it is an uncontrolled feature. So means unless and until forward breakaway voltage is achieved, the DIAC is not going to on state, whereas ACR and TRIAC, the user can control the turn on point of these particular devices. Now if you compare on the basis of commutation is nothing but the process of turning off this. So ACR we are having plenty of commutation methods like natural commutation, force commutation. In force we are having A2F commutation techniques that are available. So it is simple to turn off the ACR. Simple in the aspect that if we go for AC supplies, we have a plenty of time to turn off the ACR. Once the holding current decreases below, once the current flowing anode current decreases below holding current value, we have a plenty of time for turn off the ACR. So the negative half cycle is also available for us. But when you go for DIAC and TRIAC, it becomes complex because these devices conduct in both directions. Means if they are going to conduct for positive half cycle as well as for the negative half cycle. So as they are conducting for positive and negative, we have a very minute time. The moment at which their forward current decreases below the holding current value, from that point to the crossover point, that is the only point or the only duration that is available to turn off the devices. If we fail to commutate these devices, they remain in on condition, so they again conduct directly. It's not problem with the DIAC, but it challenges with the TRIAC that if you want to turn on at a particular point, the TRIAC immediately goes in on condition, and that is the challenge with it. That's why we are saying that the commutation for DIAC we have a less DIAC and TRIAC less time, whereas ACR we have major techniques that are available. Now if you compare on the basis of application, yes, ACR having majority of application. The challenge of TRIAC is that it is difficult to use with very heavy loads. Like if you go for inductive loads, the use of TRIAC becomes difficult. So in those particular AC application, we use ACR in anti-parallel arrangement, which works the same as TRIAC with a common gate terminal, or you can use the different gate as well. But ACR is preferred over the TRIAC because we have a time to turn off these devices. It will be difficult with the TRIAC. So TRIAC is preferred with the lighter loads, not majority of times preferred with a very heavy load, heavy inductive loads, I should say. No problem with the resistive load because the current and voltage waveform will be in phase. Whereas with the inductive loads, because of current lags, it becomes difficult to decrease the current below holding and again the negative half cycle. So that will be challenge. That we'll discuss in the next sessions of our videos. So these are references I have collected from Power Electronics, our textbook, Singh and Khanchandani. The page numbers I have already mentioned. The students can refer through this. So thank you very much for watching this. Myself Amit Naik.